Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed how the different stress condition can be achieved, intraxial test, and what are the different stresses will be developed in different planes for triaxial as well as the cyclic triaxial and cyclic simple shear test. Now, in this class, I will correlate those test conditions. Okay, so in this class I will continue how you can correlate those test condition. So to correlate that, first we have to know that when we will say that in the test condition that the failure is occurred, in liquefaction failure is occurred. So in the test, liquefaction failure is defined as the point at which initial liquefaction is reached. Okay, so in the test, the liquefaction failure is defined at the point at which the initial liquefaction is reached. So I have already discussed what is initial liquefaction, when we will say this is the initial liquefaction condition, or the at which the your limiting cyclic strain amplitude is reached. Either the initial liquefaction condition is reached or the limiting cyclic strain amplitude is reached, and generally it is normally taken as 5% in case of dense sand. Okay. So now we will discuss that means here the shear stress will develop. Okay. So that means shear stress that is developed in the different plane, different stress condition. Now this your cyclic shear stress ratio can be defined in different way in different test condition. Okay, how it can be defined? For example, for this, or you should write the cyclic stress ratio. Okay, or I can write that is CSR, cyclic stress ratio. That means the cyclic stress that is been developed. So for different tests, it is represented in different form. So for triaxial test, CSR can be defined, cyclic stress ratio can be defined. What is the amount of shear stress developed? That is half sigma d, and your consolidation pressure or stress during the consolidation is sigma 3 dash. Okay, you can write dash. So now it is effective. I am writing that half sigma d divided by sigma 3 dash. Now for cyclic simple shear, CSR is written at tau h, okay, or sometime written as tau cyclic also. So that is tau h divided by sigma v dash, because that is the stress during the consolidation. So as I mentioned so that means the cyclic simple shear test, the field condition can be simulated easily. In the field also, the consolidation stress is sigma V bar. So here also this is sigma V bar or dash, and intraxial it is sigma 3 dash. Okay. So this way it is been represented. Now I have to correlate these two CSR, two test conditions. How I will correlate that? So for that condition, Seed and Recock, they have suggested 4 controlling factors. So one by one I will discuss all these 4 controlling factors. So first controlling factor is the maximum ratio of the shear stress developed during cyclic loading to the normal stress during consolidation on any plane in the sample. Okay. So now if this is the condition, now we have 2 cases, triaxial. Now triaxial, what is the shear stress developed during cyclic loading? Which is a ratio. Why the maximum? Maximum means the maximum shear stress developed. Okay, so that means basically the maximum shear stress developed this is the maximum ratio. So that's why the intraxial, the shear stress, actually the shear stress developed during the cyclic loading. So how much shear stress developed during the cyclic loading? For triaxial, shear stress developed during cyclic loading is half sigma d, and the normal stress during consolidation. So normal stress during consolidation is sigma 3 dash, because on that plane normal stress is sigma 3 or sigma 3 dash. Okay. So that means if I take that plane, that your where the shear stress is developed, on that plane normal stress was during consolidation. Suppose if you go to this stage, so this is the plane I am talking about, where the maximum shear stress is being developed. So this plane, we are taking the shear stress developed divided by normal stress during consolidation. So if you look at this thing, this is the shear stress developed during cyclic loading to the normal stress during consolidation on any plane. And why I am taking that plane? Where it is giving the maximum ratio. So that means I am taking the plane where maximum shear stress is being developed. That plane I am taking, because it is on any plane. Clear? So I am taking that plane. So in that plane, your shear stress developed is half sigma d, and on that plane normal stress during consolidation, because this is your stage during consolidation. Okay. So during consolidation, normal stress on that plane was sigma 3 or sigma 3 dash, and the shear stress developed on that plane is half sigma d. So I can write that this is for triaxial half sigma d divided by sigma 3 dash. Okay. Or you can write half sigma d by sigma 3 also. Now for simple shear, so simple shear, if I go to this plane, say in this plane, so this is the plane. So if I take this plane during the consolidation, this is the plane where sigma h is developed, and during consolidation, this is consolidation normal stress is K0 sigma v dash. So I will take this plane. So if I take this plane, so then I can write this is sigma h divided by sigma v dash. Okay. Now these two things, now the same condition we are writing for two different cases, triaxial and simple shear. So now we can equate them, because this is the two equal condition. So I can write that my tau h by this is k0. So this is the k0 plane I am taking. This is k0. So tau h k0 sigma v bar dash will be equal to half sigma d by sigma 3 dash. Okay. So I can write that for tau h, because how they are representing actually CSR, this is tau h by sigma v dash, and here half sigma d by sigma 3 dash. This way these two CSR been represented. So I have to convert this way, sigma h divided by sigma v dash or bar. This is equal to simple shear. That is equal to, will be k0 and half sigma d divided by sigma 3 bar, that is for triaxial. Clear? That is for triaxial. So that means I can correlate these two CSR, the CSR for triaxial and CSR for simple shear, in this way by using first controlling factor. Now come to the next controlling factor. So what is next controlling factor? The maximum ratio of the change in shear stress on any plane during cyclic loading to the normal stress on that plane during consolidation. So that will be the same, because now this condition for triaxial, so triaxial, the change in initial shear stress was 0, then the level of shear stress is half sigma d, half sigma d. So change in shear stress will be half sigma d, so it will be half sigma d, on that plane divided by normal stress acting on that plane during consolidation. So again the normal stress is sigma 3 bar or sigma 3 you can write. Now here it is, now for simple shear, again the initial shear stress was 0. Now the level of shear stress is tau h. So that's why change in shear stress will be tau h, and this will be k0 sigma v bar. So now if I correlate that, again I can write that tau h k0 sigma v bar is equal to half sigma d divided by sigma 3 bar, or tau h divided by sigma v bar for simple shear, that is equal to k0 into half sigma d sigma 3 bar triaxial. Okay, the same. So that means the controlling factor 1 and 2, the relationships are same. Now go to the controlling factor 3. What is written here? The ratio of the maximum shear stress. Here it is not the maximum ratio, it is the ratio of the maximum shear stress induced in a sample during cyclic loading to the mean principal stress on the sample during consolidation. So what is the difference? Previous case it was to any plane. That's why we have taken this plane. Okay, so yes, any plane. So now it is the maximum shear stress induced on a sample during cyclic loading to the mean principal stress on the sample during consolidation. So if your triaxial, So what is the maximum shear stress induced in the sample? For triaxial, what is the maximum shear stress? Because we have taken 45-degree plane, so that will be give the maximum shear stress. So maximum shear stress will be half sigma d. And what is the mean principal stress during consolidation? So mean principal stress during consolidation, so all the stresses is, so mean principal stress mean sigma m bar. So that is equal to 1 by 3 sigma 1 dash plus sigma 2 dash plus sigma 3 dash. So but during consolidation on a triaxial sample, all the stresses were sigma 3. So the sigma 3 bar will be the sigma 3 only, because all the stresses were during the consolidation of triaxial sample, all the stresses were sigma 3. Okay, so it will be sigma 3 on the sample. So on the sample, all the stresses were sigma 3 only, sigma 3 during consolidation, sigma 3, sigma 3, sigma 3. So if I add them, I will get sigma 3 plus sigma 3 plus sigma 3 divided by 3, it is sigma 3. So it will be sigma 3 only, or sigma 3 bar. So this is for the triaxial. Now for the simple shear, the maximum shear stress developed in a sample, so what is the maximum shear stress developed in a sample? So this is the amount of maximum shear stress developed in a sample. This is the maximum shear stress developed in the sample. This is the maximum shear stress in the sample. So I will consider that stress, maximum shear stress. So this is equal to tau h square plus half sigma v dash 1 minus k0. That is maximum shear stress developed in the sample divided by the mean effective stress during consolidation. So during consolidation, this was sigma v dash in vertically, and radially it was k0 sigma v dash. So I can write the mean effective, this is for triaxial. So mean effective principal stress or mean principal stress during consolidation will be sigma m bar, that will be 1 by 3 sigma v dash plus k0 sigma v dash plus k0 sigma v dash. So this will be 1/3 sigma v dash into 1 plus 2 k0. This is for simple shear. Okay, so that means here this is the mean principal stress ratio, that will be sigma v dash 1 plus 2 k0. So now we will equate them. Okay, now if you equate them, so this will be simple tau h square plus half sigma v dash 1 minus k0 divided by 1/3 sigma v dash 1 plus 2 k0. Okay, that is equal to half sigma d divided by sigma 3 dash or sigma 3. Okay, so now I can write the same tau h divided by sigma v bar for simple shear. This will be equal to, so how will get that? So here this is half sigma d divided by sigma 3 bar, that into this one. 1/3 sigma v bar 1 plus 2 k0. Okay, now we have to square them. So you have to square it. Okay. Now if you first multiply these two terms, then square it. Okay. Then you take this side, this side. Okay. So then it will be sigma. If you divide it by sigma h, so this will be sigma h, or if I simplify it, you will find that. So this one, this I divide it, or let me just simplify it, it will be easier for you to understand. So I can write another step, say. Okay, so I can write that is your tau h and square divided by sigma v dash square. Or this is square, then if I take sigma v, if I divide this tau h square divided by sigma v square, then this will be simple half 1 minus k0. Okay, simple 1 minus k0. Now if this is under root, this is whole is under root. Okay, now if I square them, then this will be equal, this will be square. Okay, now if I write tau h sigma v bar simple shear, so this will be simple. Now we have to take this is this side, so this will be half sigma d divided by sigma 3 dash into 1/3 sigma v dash 1 plus k0. Okay, this is square, this is square, then minus this term, then minus, it will be half 1 minus k0 whole square, and that is under root. Okay, that is under root. So this is simple shear. Now if I express them in like the previous cases, so I can further express them. Okay, so this controlling this equation I will discuss later on. So first express them in this equation. This is for continuation of the controlling factor 3. Okay, so this is tau h divided by sigma v dash simple shear, that will be equal to, if I take half sigma d sigma 3 dash outside to the root, then this will be half sigma d by sigma 3 dash triaxial, that will be into root over this is, you can see this is 1 by 9 sigma v square, oh there will not be, yeah, sigma v square is there, So I have taken half sigma d into sigma v, and if I take sigma v, one more thing, then this term will not be there, because I am dividing it by sigma v dash. So this will be tau a square sigma v dash, sigma v dash, then this is sigma v dash. So this sigma v dash will, this is the square within the root, sigma v dash square. So this will cancel. So there will be not sigma v bar. So this sigma v bar will not be here. Okay? Because I am dividing it sigma v dash square within root. So that I have to divide it by sigma v dash in the denominator also. No? So that's why this, and then I am multiplying it with this one, then I am squaring it. So this is 1/3 sigma v plus 2 sigma 0. Yeah, 1/3 of, yeah. So this is minus sigma v. Yeah, fine. So now I can write, so this is your within square 1 by 3. So I can write, this is 1 by 9, 1 by 9, 1 plus 2k0 whole square. So you can see this is, I am taking, this is outside. Okay, this term is outside. So this is 1 by 9, 1 plus 2k0 whole square, 1 plus 2k0 whole square minus, this is 1 by 4, 1 by 4, 1 minus k0 whole square, then divided by, only in this, divided by only this portion, half sigma d by sigma 3, sigma d by sigma 3. Okay. So this is the equation. This is the whole thing is under root. This whole thing is under root. This is 1 by 9, 1 plus 2 k0 square minus 1 by 4, 1 minus k0 whole square divided by, because I have taken this portion outside. So it will be divided by half sigma d bar, or this is square. So whole portion is, so this is square, so this will be also square. So whole this portion will be outside the, within the root. Okay. So this is my controlling factor 3. Actually this is for case 3. Now for case 4. I will discuss about the case 4. What is case 4? Case 4 is giving the ratio of the maximum change in shear stress on any plane during cyclic loading to the mean principal stress on the sample. So for the triaxial, for the triaxial, ratio, maximum change in shear stress. Okay. Again the change in shear stress is, a maximum shear stress is half sigma d, and the mean principal stress during consolidation is sigma 3 dash. There will be no change, the same one. Now for simple shear, this is change in shear stress, maximum change in shear stress, again on any plane. So it is not the maximum shear stress, it is the change in shear stress on any plane. So previous third one is the maximum shear stress on the sample. That's why I have taken tau max. But here it is now again any plane. So if it is any plane, then this is the plane, change in shear stress will be tau h. And okay, so change in shear stress will be same as tau h, and your mean principal stress, this is mean principal stress for simple shear, so it will be half sigma d dash 1 plus 2 k0. So that means first case it was any plane, second controlling factor it is any plane, third case it is on the sample. That's why in the third case we have taken tau max, maximum shear stress, and other three cases it is any plane. There also it is maximum change. Maximum change means 0 to maximum shear stress, that is the maximum change. So that's why I am taking the maximum, that's why I am taking the plane where the developed shear stress is maximum. So that's why I am taking that maximum shear stress always in case of triaxial. But in case of simple shear, I have to take the any plane. So that's why I have taken first two, three cases, first one or two and the fourth cases it is any plane. Change in maximum shear, change in shear stress. So shear stress is tau h on that plane. So change, maximum change will be 0 to tau h. So it is tau h only. Okay? So that's why this is, here also it is written the maximum ratio. That's why I am taking the maximum shear stress. That's why it is written maximum ratio. Ratio of the shear stress. That's why taken. But as it is any plane, so in simple shear it is taken tau h, not tau max, because it is on any plane. But here, in case of 3's case, it is in the sample. That's why it is taken max, tau max, in case of simple shear. Clear? So now this is the simple shear case. So I can write that if I equate them, then half sigma d, so if I have to equate them, then I will write tau h divided by half sigma v dash 1 plus 2 k0, that is equal to half sigma d divided by sigma 3 dash. So from here I can write that tau h divided by sigma v dash simple shear, that is equal to this will be again 1/3. This is 1/3. This is 1/3. So it will be 1/3 1 plus 2 k0 into half sigma d divided by sigma 3 for triaxial. Okay. So that means now I am correlated. I have correlated this all these 4 factors. So now if I generalize them, so I can write that tau h divided by sigma v dash for simple shear, that is equal to alpha time of half sigma d divided by sigma 3 dash for triaxial, where alpha is equal to k0 for case 1 and case 2 also k0. So alpha will be k0 for case 1 and case 2. Now alpha will be how much? Alpha will be this term for case 3. So alpha will be equal to root over 1 by 9 1 plus 2k0 whole square minus 1 by 4 1 minus k0 whole square divided by half sigma d by sigma 3 whole square. That is for case 3. Okay. So you can see this is case 3. Now this is equal to, for case 4, it is simple, 1 by third 1 plus 2k0. So it is 1 third 1 plus 2k0. This is for case 4. Okay. So now I can correlate the simple CSR of simple shear stress, simple shear test, cyclic simple shear test with the CSR of cyclic triaxial test by using these equation or these correlations. That means the CSR of simple shear or cyclic simple shear is equal to alpha time of CSR of triaxial or cyclic triaxial. Okay, because this CSR is written in this form, half sigma d by sigma 3 dash for triaxial and tau h by sigma v dash for simple shear. So now the simple shear CSR, cyclic stress ratio, is expressed or can be determined if I know the simple shear of the triaxial, if I multiply the if I know the CSR of the triaxial, you have to multiply with alpha. Now this alpha value you can get in this from this table, that for this is the reference. Now if case 1 the alpha is equal to k0, for case 1 and case 2 you can see that if k0 is equal to 0.4, alpha is for case 1 is the same as k0. Okay, and for case 2 and case 4 also it is easy to determine because it is only 1/3 1 plus 2 k0. If k0 is 0.4, it will be 1.8 divided by 3, so it will be 0.6. So this is 0.6 for 0.4. But determination of alpha for case 3 is slightly difficult. So that's why few cases it is been determined and it is been reported here. If k0 is 0.5, for case 3 alpha is 0.25, and for 0.8 it is 0.83, for 1 it is 1. And remember that for case 3 when alpha value is determined, half sigma d sigma 3 is taken as 0.4. So this table will give me the alpha value, and correlation you will get from here that simple shear CSR is equal to alpha time of CSR of traction. Okay. So now in this lecture I have correlated the CSR value of simple shear with the CSR value of traction. Okay. So in the next class I will correlate this lab test result with the field test result. Okay. Now it is lab test results are being correlated. Now it will be correlated with the field test. Then we will discuss how we will get that actual tau h, that is the stress level required to cause the initial liquefaction. Thank you.